Hello, welcome to the next part of the lecture focused on the introduction to big data principles. In the previous part, we looked at what are the ways in which people have defined big data, how did the concept of big data evolve over a period of time, and how it's not just a specific technology or a specific set of uh, keywords, whereas it's actually got a very deep set of meanings associated with being able to process very large scale data at very fast velocity, irrespective of the complexity and irrespective of what language or what mechanism or tool that you choose. So, in this, let's kick it off by understanding why bother with data at all in the first place. And then we will get to how big data plays a very critical role to answer this question. So, if you look at how data is being used historically, right from pretty much the first instances of data collection that have ever happened by the earliest of um, uh, diary recording um, professionals. There has always been this need to look at that data that's collected and recorded in notebooks and diaries to come back and look at what happened. And that's what we in the world of data analysis call as reporting. And I believe the first such meticulous instance of um, reporting was conducted by, I believe, Florence Nightingale back in the day during the World Wars. But obviously, there are many other instances even prior to that, starting from even some of the earliest potentially human beings who walked the earth, right? Reporting has looked different in various shapes and forms based on the industry, based on the domain, and based on the time period as well, right? Some of the earliest instances uh, didn't really have visuals, right? It had more an intrinsic weaving of annotations with markings, with some kind of visual drawings, etc. But some of the more modern representations of reporting pertain to being able to use visuals, being able to use uh, tools that bring out the natures of the data by plotting various dimensions of the data on different forms of geometric patterns. Any which way, reporting pertains to what happened. Then the question came to uh, trying to understand what can I do that can change what happened. Obviously, you can't go back in time, but you could look at ways in which what happened could be continuing to happen or could have repercussions about what's going to happen. But to even get to that stage, we need to first understand why did it happen. And here's where the analysis really comes into play. So here we start to talk about a lot of ad hoc discovery style exercises, sometimes aided by tools like Excel sheets, sometimes aided by what's called as business intelligence tools. Um, but in any which case, the analysis yields interesting insights, and those insights become the basis for um, trying to see whether we could start to control those circumstances in some shape and form. Excuse me. If you now have the mechanism to understand why something happened, then the natural question to ask is, could it happen again? And the extension to that question is what will happen in the future, and that's where predictive models start to come into play. And here there is, of course, a lot of work that has gone into creating machine learning training courseware, be it on um, online like course providers like Coursera, edX, and so on, but also a lot of training institutes across even in India. So the focus has been for most of these coursework building machine learning models which can predict, given a particular piece of data, what's likely to happen, given past instances of the same data and outcome combination. So that's classically called as supervised learning. And most predictive models that you see out there, which are being taught, or instances of model supervised learning. So predicting is about what will happen. But then none of these three questions are really changing the way that the real world operates. Right? It's about reporting analysis and it's about predicting. Whereas what really changes how a particular course of action, a particular course of events evolve is the action that gets taken on top of these predictions. It's the action that that you have the ability to do if you know what's actually going to happen or what's likely to happen. And in this kind of a scenario where you need to take action, you have to be able to look at um, all the previous questions that we just spoke about, but also combine that with what is actually happening now, right? And that's what's called as operationalizing. It's not really an English word, but it's a gerund we can appropriate for these circumstances, right? So what it really means is, can I take insights which are being generated by analysis or generated by machine learning models which are predicting outcomes, and then go do something about it based on what is the current circumstance. So if you take an example of a prediction which says that given a bunch of data about speeds of vehicles on a busy intersection in a city or in a highway, there is a possibility that there is an accident that's likely to happen. Now, that kind of analysis could be done just by looking at past instances of accident data at that same intersection. You could even think about building some kind of a propensity model or a prediction model, which, given a bunch of data which has been recorded in the past, picks up the patterns. It could be a combination of speed, it could be a combination of time of day, density of vehicles, whatever, right? So that kind of a predictive model will be able to um, generalize into some kind of a learning that it's able to put together patterns of these different data points and predict that there could be an accident. But then that's only based on what's happened in the past. So if you want to operationalize this, you could look at taking that kind of a model, feeding it live data from that same intersection, and that live data comes from an operational system, right? Comes from systems which are collecting data in real time, like a CCTV camera or the traffic policeman just making notes dynamically in a mobile application. Um, and that data gets fed instantaneously to that particular machine learning model. And the model predicts whether there's going to be an accident now, right? So with that kind of an output, then the traffic policeman could take some dynamic calls, like for instance, um, controlling the frequency of um, uh, the green signal for a specific direction of traffic, which has a very high probability of accident. So that's what I mean by operationalizing. You take the model or you take the analysis outputs and you make it live, you make it real. And in the context of what is happening, you collect the data in real time. Sometimes it's delayed by 5 seconds or 10 seconds, or maybe even a couple of minutes. But then the link to that operational system which is collecting data is crucial because that's what makes it live. That's what makes the action relevant. What should not happen is, you predict all of this, and then you use the model to look at what's happened during the day, and at the end of the day, the model says, yeah, there could have been an accident at 10:30 in the morning. That doesn't help anybody, right? It's too late. So the real-time angle here is a critical aspect of operationalizing. And then finally, you need to be able to activate. And the difference between operationalizing and activating is the fact that operationalizing is about what is happening now, and you still have humans take some action on top of it. But activating is where you make it happen. So here we're talking about automation, which takes the complete cycle all the way through to taking outputs of the machine learning model or the analysis and getting it deployed at the traffic signal such that there is no human involved in the loop. So if you take the same example of that accident prediction, you would want in this activating scenario for the machine learning model to be rigged up to the sensors which are controlling the traffic signal, such that the moment the ML output is predicting a very high chance of an accident happening in that direction, um, it, it triggers some kind of a threshold, and since it's crossed the threshold, it triggers an action, and the action goes and changes the traffic signal for that direction of traffic. That's activating and that's automation. So if you really think about it, then the goal of data science, in my view, should be to actually make activations possible, completely automated, right? Without having humans involved to either interpret the outputs, humans involved to make sense of, what does this prediction mean, or humans involved to take the insight that's being generated by the model to go operationalize in a specific setting. So imagine if you just remove humans from all of that, all of those steps, and have data science directly inform what needs to happen to an operational system and have the operational system take action automatically. That is really powerful. So why bother with data? To me, the question should be answered as because we can make something happen automatically and improve something about the real world. And accident is just one problem statement. There are so many problem statements, so many domains, starting from extremely complex problem statements like cancer research, protein folding, and things like that, all the way down through very practical, simple applications of fraud preventions and so on. So that's data, right? That's data science. Now, does this process change because data is large, or because the data is very large, very high velocity, or because the data is not of a standard shape and form? It's not relational. It's got multiple structures. The answer to that is no, right? And it kind of makes sense intuitively. Why should the volume of data dictate whether you could actually have a real world impact from that data? It need not, right? It absolutely has no connection at all. Um, why should the velocity of data have a bearing on whether we could make something happen based on that data? Absolutely no connection at all. And why would the complexity of the data matter at all? Because that's just a very simple technical problem statement you could just solve using the right tool. But what does happen though, right, is the fact that the tools change. It's no longer feasible to do all of this that we were just talking about by having, for instance, just mobile phones, right? If the data was really small, if all you needed to do was just punch in, um, few variables and you get some answers, you could just do it on a mobile phone. Nowadays, mobile phone CPUs are super powerful, right? It's as powerful as how my desktop was back in the day when I was in college. So obviously, that kind of a device today is not conducive for being able to deal with very large volumes of data or velocity of data. So the tool has to change. And in doing so, in changing the tool, we now get access to a plethora of strengths, right? A plethora of really interesting capabilities, which makes us capable to go from data all the way through activations. That's the reason why we are assembled, right, for this course. Because what we will focus on for the rest of this course is what are these tools? What are some examples of these tools? How are these tools changing the way that you can operate with large volumes of data, like high velocity, etc., complexity? And most importantly, how do you go from using a tool to analyze, using the tool to build predictive models, to finally using tools to operationalize at very large scale, at very high velocity, without being affected by the complexity of the data, such that you could make these activations work for you. So if you're able to do that at very large scale, then you've truly mastered applying big data to data science. And if you look at why is that problem statement important, I would say pretty much every single successful B2C brand that you work with today, be it Myntra, be it IRCTC, be it the income tax portal, be it all kinds of very large consumer-oriented services like Swiggy, Ola, etc. All of them have mastered this practice, right? All of them have benefited from being able to use data sets at very large scale and activating it. Activation is very important. So let's dive deeper into this now. So big data in the era of cloud has actually become even simpler. What we spoke about in the previous video were instances of how big data evolved over a period of time as it graduated from a single company, from a closed source academic research paper from Google through open source at Yahoo, open source at Twitter, and being adopted at the likes of Facebook and Netflix and so on. So um, that was the journey um, before um, Salesforce and Amazon completely disrupted the era of information technology and hardware. So, right at the time when big data was catching up, or rather was becoming popular, cloud had already made inroads into certain types of companies, especially startups, because startups could not afford setting up big data centers or renting spaces and starting to dedicate them machines and networking and all the stuff that you would imagine from physical infrastructure. So all of that became very expensive for um, startups which wanted to be nimble or which didn't have much funding. So cloud became very attractive for those kinds of startups because you could just start off with a device and not have to pay the enormous amount of money that is involved in investing to the device if you were to just procure it on your own. But you could just rent it, right? So that kind of a shift in pattern of how hardware was consumed really disrupted big data as well. But we will talk more about that in the cloud lecture, which is the next lecture. But from the perspective of big data, what happened was the architectural pattern that underpinned how big data was originated became extremely conducive for adoption of the cloud. What I mean by that is, we spoke in the previous video about how Google launched two papers. The first was what's called as the Google file system, which talked about how you could use um, disks across multiple different types of commodity machines and clusters of those commodity machines to achieve storage of very large volumes of data without having to worry about cost. Right? That was their first paper, and they used that. They branded it as Google File System because they built the GFS for their internal purposes. And the second paper was the Google MapReduce, right, which talked about how you could then use the CPUs of those same clusters of machines, commodity machines, to go process the data that's actually residing in those disks of those commodity machines. So if you really look at what happened in that kind of a thought process, you effectively separated out the storage of the data from the compute. The compute meaning the data processing needs. So this became an actually fundamental pattern, right, to how big data started to get processed, or big data technologies became popular. Now, why did it become very fundamental? Because it allowed you to operate without having to know about where the data is stored. It allowed you to treat resources as completely decoupled, right? So that you could scale each of those independent set of resources completely, in a manner decoupled from the other resources. So what I mean by that is, if you had disks in a in a in a machine, and those disks have a storage space of a terabyte. Now, if that machine had just two CPUs, that's all right. You could still leverage those two CPUs to make some progress in data processing, and you could leverage all that 1 terabyte of space to actually store your data. In another machine, you could have just 100 gigabytes of storage, but you could have, let's say, a GPU, and that's okay, right? You could still process data, you could still store data. It's just that the scale is different. The scale is smaller of the data storage, but the scale of data processing is lot more powerful. But the foundational aspect of the data processing that you need to do remain the same for both those machines. What I mean by that is, I'll illustrate with an example. So let's say all we were doing was just counting the total number of ticket bookings. Like we'll go back to that Indian Railways example. So we want to be able to count tickets that are booked in a day. And the tickets that are booked in the South Zone are stored in a really powerful machine. The first machine that we spoke about, 1 terabyte of storage, but only two CPUs. The tickets which are booked for the state of Goa are stored in that second machine, just 100 gigabytes of storage, but a GPU available for you. If what you wanted to do was count the total number of tickets which are booked, you could run that program. You could write the program firstly as just a simple count operator in a Python, let's say in a simple Python program, and you could run it on both those machines, and you would know for a fact that the program will finish. Right? In the first instance, the program might take a little longer because it's got a weak CPU, but it's got a really large storage space, relatively speaking, compared to the second machine. But nevertheless, it's the same Python program running on two machines and still making progress and getting you the answer over a period of time. So that's why I'm saying the ability to think about the functionality of the program, in this case, a Python program to count, as decoupled from the kind of resource that's actually available for you to compute, makes it really powerful to independently plan and separately execute that particular program across both of those machines and get the answers that you want. But you would still need to be able to know that these two machines are part of your cluster. The data is actually spread across uh, all the disks corresponding to that 1 terabyte of storage in machine one, because that could be itself spread across 10 disks, right? Each disk is capable of storing 100 gigabytes as an example. And there could be 5 disks in machine two, but only one of it is dedicated to the cluster, which is the 100 gigabyte disk. The remaining 4 disks, each of 100 gigabytes, could be used for something completely different, not related to data processing for ticket booking. It could be used for operating systems, could be used for storing, running the web application, whatever, right? So you still need to be able to know that one disk in that second machine is part and parcel of the data cluster, such that we need to be able to launch programs on top of it. So you need a way to understand how the resources are spread. You need a way to know where the data is placed, and you also need to be able to know what compute is available, right? Whether it's two CPUs, one GPU. But ultimately, what matters is parallelism, um, because the moment you have two CPUs in one machine and a GPU in another machine, each is independent of the other. Each has its own power, right? Which means you can just independently run those CPUs and get the answer that you need. So imagine you can run the same Python program that I was just talking about on both those machines independently, and you'll get the count of South Zone tickets, you'll get the count of Goa tickets, as and when they come in, doesn't matter how much time it takes, but they're all operating independently. So that parallelism becomes critical for how you process large scale data over a period of time. Now, this kind of a parallelism that we just spoke about is what's called as embarrassingly parallel computation, because you know for a fact that Goa's tickets are in the second machine and South Zone's tickets are in the first machine, ticket bookings. So you could just run each of the Python programs independently and get the answer for how many tickets in South Zone, how many tickets in Goa. The two machines need not talk to each other, right? So it's as though you just took a copy of the Python program, ran it on both the machines, and ran it in parallel. You allowed it to finish, and you came back and you got the answer. That's it. Nothing more sophisticated is involved. That's why it's called as embarrassingly parallel. And this kind of a model of how the data split and you get to do this parallel computation gives you complete flexibility on the type of compute, type of storage we saw with these two examples. With that, I'll pause this video, and we will look at how the different paradigms of big data evolved and what the fundamental principles are in more detail in the next video.